So let's analyze the question for midterm number 1. One question says, if an object has a positive acceleration, which of the following statements is true? From the wording of the problem, we know that acceleration is positive, and immediately we remember that the acceleration is the change in velocity over time. So that means that the change in velocity is being positive. The change in velocity is the final velocity minus initial velocity, and that means that final velocity minus initial velocity is larger than 0. In other words, that the final velocity is larger than initial velocity. That means that velocity, it's increasing. Now, from this answer A, we see velocity is increasing and positive. The second one is velocity is increasing but not necessarily positive. Let's analyze if that is actually the case or not. Let's say that there is a car that it's traveling in -5 meters per second, and an instant later is traveling at -3 meters per second, and we define as positive direction x towards the right. If I want to calculate the acceleration, of course, I'm going to find that final velocity is 3 minus initial velocity, which is -v, and then divided by time. Let's say that it takes that the time it takes is 1 second, just to make things simpler. So that's going to be -3 minus minus, that becomes plus, so that's -3 plus 5 divided by 1, which of course is 2, divided by 1, which is equal to 2. This acceleration is positive, but these velocities are not positive. In fact, are negative. So not always the fact that an acceleration is positive implies the velocity is positive. That acceleration is positive simply means that the velocity is increasing, which is what we're observing here, and velocity is increasing here, but not necessarily positive. So the right answer is, of course, option B. The object's position must be increasing. That's not necessarily the case. In fact, in here we see that the object is moving towards the negative side. So this is 0. This will be like 1 meter. This could be like 2 meters, 3 meters. So in fact, we see that the object is going towards smaller. And then the object's displacement might be increasing. Again, is not necessarily the case. The object is actually decelerating from the point of view of the negative axis. If we go it from the positive view, from the view of the positive axis, the object is of course coming to stop, or maybe it's actually returning. But in any case, the velocity is increasing. That's certainly the case because -3 is larger than -5. The velocity is not necessarily positive. Acceleration sign only tells you what is the direction of the change in velocity. So I had a vector -5 going like this, then I have a vector -3. What is the difference? Well, I have a positive vector, which is acceleration. So that's the initial and final velocity. So with respect to question number 1, let's see more questions. What is the role of coordinate system in describing motion? This is a matter of definition. That's why it's important to first study the concepts and then go to the problems. If you do not understand the concepts, it's impossible to apply them in the problems. The difficulty in physics, of course, is in actually training our intuition, not to jump into conclusions or bias that we have because the way that we observe the world, right? We have to be able to abstract and read within the things from the natural world. And so this question is asking a question about concept that we introduced in chapter 1, which is the definition. The coordinate systems in describing motion. Because motion is the relative change of position of one object with respect to another in time, we need to describe what other object, or what is that object with respect to which we are describing the motion. So that's actually our frame of reference. And from our frame of reference, we build what we call the axis of coordinates, or the coordinate system. So of course, if I am on the station and I see a train pass, I'm going to define my own axis of coordinates. For the guy who's running the train, riding the train, he is going to be defining a different axis of coordinates that actually is moving with its train. So in reality, we can choose any coordinate system that we want. The coordinate system is arbitrary. It is based on convenience, but it does help to uniquely define an object's position. That is actually the definition. There's nothing here to reason. It's just actually, you can reason why the options are wrong. But the coordinate systems are essential and must be for all observers. We see that's not the case. But the coordinate systems define objects' absolute motion in space. That's ridiculous. There's no absolute motion in space. We saw that in chapter number 1. So the only question will be coordinate systems are relevant and do not affect the description of motion. They indeed do not affect they do affect the description of motion because all positions are going to be based in our x, y, or our x and y prime. And the description of the motion is different. For this guy, the train is moving, but he's stationary. For this guy, the guy in the station is moving, and the train is the one that's stationary. It's not, it does affect the description of motion, but motion is still the same. So coordinate systems are arbitrary, yes, they are chosen based on convenience, but they help uniquely define an object's position. This is a matter of definition, and that's why it's important to study the concepts to be able then to apply them in your problems. Next question says, a basketball player jumps to a maximum height of 1.8 meters. Assuming the acceleration due to gravity is 10 meters per square second, what was the player's initial velocity? Now this is a classical example of kinematics, so we can write our equations. Final position is 1.8 meters, initial position is 0. It jumps from ground. The final velocity is, of course, 0. Why? Because it's the maximum height. If that was not 0, if it was positive, then the guy would keep going higher. And if it was already negative, the guy would be already falling. So at the point of maximum height, velocity is 0. What is the initial velocity? Well, that's actually what we're trying to find. What is the acceleration? That's going to be minus 10. And what is the time it takes? We have no information. So what equation do we use whenever we have this sort of situation? We could not use the equation that says that v is equal to v sub 0 plus 8 times t, because we have no clue about time. So the equation we're going to be using, of course, is the kinematic equation in one dimension. This says that that v squared is equal to v squared sub 0 plus 2a delta y. Now we need to replace the final velocity 0 squared, the initial velocity we don't know, the acceleration is minus 10, and the change in position is 1.8. So from here we have minus 20 times 1.8, that's minus 36. So we can keep going. V sub 0 squared is equal to 36, which of course v sub 0 is equal to 6 meters per second. So option C. Important again, write the equations, find out what's missing, and based on what's missing, you choose the equation to use, which is this equation here. Whenever you don't have information on time, we use this equation. We've done it a million times. This is one more trivia. Next question. A boat can move at 30 kilometers per hour in still water. So we know that the velocity of the boat, I suggest that you write it, it's 30 kilometers per hour. And it says how long will it take to travel 12 kilometers. So we wanted to cover the distance of 12 kilometers, let's say. And how long does it take? If it's going upstream in a river flowing at 6 kilometers per hour. Now we've seen many cases where we have the river and the river is flowing and I have a boat and I say, oh, I want to go from here to there. But this is not what the problem is saying. The problem is actually much more simple. It's saying how long will it take to travel 12 kilometers upstream? What does upstream mean? Well, it means upstream, which means going opposite to the current. So actually what we're having is not this scenario. What we're actually having is this flow. If you wish, the river is flowing that way and we're going contrary to the river. Right, so that's going to be the water, and this is going to be our boat. So let's analyze the information that we have. The river is, by the way, we forgot to say here, the velocity of the river is 6 kilometers per hour. Now, of course, this is a problem in relativity, and we know that the two equations that we use in relativity is we have to identify the object. We identify a reference frame 1, and we use a reference, frame 2. What's going to be the object? That's going to be the boat. What's going to be the reference frame 1 is going to be the water of the river. And the reference frame 2 is going to be the ground. For ground, we would use G. For water, we use W. For boat, we use V. And then we can write the equations. It's going to be that the boat in the ground system is defined as the sum of the boat in the water plus the velocity of the water with respect to the boat. With respect to the ground. Right? So, oh nice. With respect to the ground. So, first thing, how do we identify the velocity of the river? Well, the velocity of the river is the velocity of the water, but it cannot be with respect to the water because nobody is moving with respect to itself, right? So it needs to be the velocity with respect to the ground. And that's going to be 6 kilometers per hour. And what about the velocity of the boat? Well, the velocity of the boat is actually the velocity of the boat with respect to the water. We typically, unless it's explicitly said otherwise, we assume the velocities of the objects are given in the medium in which they travel. If it's an airplane, it's the relative with respect to the air. If it's a boat, it's with respect to the water. If you're in the airport walking in one of those ways that go faster, that's the velocity in with respect to the walkway. Anyways, in this case, the velocity is 30 kilometers per hour. And so it becomes just trivial just to realize one thing. Upstream means that we're moving against the stream. So if we define the positive direction as going against the stream, and this is up to you, that will be negative. Otherwise, it's going to be positive. But in any case, the signs are different because I'm going upstream. So what I'm going to find is the velocity of the boat with respect to the ground is going to be the velocity of the boat with respect to the water, which is 30 kilometers per hour minus the 6 kilometers per hour of the boat. That's going to give me 24 kilometers per hour. And once I see that, then I can say that what is the velocity, what is the time? Well, the time is distance divided by velocity, and so that's going to be 12 kilometers in 24 kilometers per hour, and that's going to be equal to 0.5 hours. 0.5 hours is 30 minutes. So going upstream at that velocity takes 30 minutes. Next question says, ball is thrown horizontally from top of a 20 meters building. with an initial speed of 15 meters per second. So that's going to be 20 meters, and the velocity is 15 meters per second. And of course, that's the initial velocity. How far from the base of the building does the ball fall? So we've seen a million times this. There's going to be a parabolic shot. But this is one of those. Actually, this is probably one of the most difficult problems in the entire test, which is trivial in any case, because once we have a motion in two dimensions, we remember we have to decompose it to vertical and horizontal components. And now we're going to have to find horizontal components. We're going to identify the information okay, and acceleration. Let's go for the horizontal component. So first of all, we have an initial velocity which is 15 meters, but it's only 15 meters going in horizontal. But then that means that v sub x sub 0, it's 15 meters per second. V sub y sub 0 is 0 meters per second. So this is the first thing to do, is just take the vector and decompose it into horizontal and vertical components. Why? Because it's thrown horizontally. It's thrown horizontally with 15 meters per second. It means that the entire thing is 15 meters per second. If you want to decompose with SOHCAHTOA, then use SOHCAHTOA and realize that the adjacent goes with the cosine, and the cosine is cosine of 0. Why? Because it doesn't make any angle with respect to itself, with the x-axis. The velocity and the axis are aligned. So theta is 0, therefore cosine of 0 is 1, right? But anyway, it is aligned. The entire component of velocity is horizontal. So what is the final velocity? We don't know. That's the question we're being asked. What is the initial velocity, position, excuse me. We can take it as 0. We're going to take the origin of coordinates of the building because it's much more convenient. What is the final velocity horizontal? Let's say we don't know. What is the initial velocity? Well, the initial velocity is 15. What is the acceleration in x? Well, there are no forces acting in the horizontal component because there's no friction. We take that to be 0. And what is the time? Well, we don't know that one. In fact, as everything, as always, excuse me, the problem is going to be about finding time in the vertical motion and plugging it here to find the x component. Now, of course, we know immediately, because the acceleration is 0, that the initial and final velocity are the same. So if you notice, you write it. Otherwise, that thing just simply comes from the fact that v is equal to v sub 0 plus a times t. When t is equal to, excuse me, when acceleration is 0, that means that v is equal to v sub 0 for every time. So that means that it's going to be 15. But if you don't realize, it's fine. You don't need that information. Then let's write the information that we have for the final velocity. Now, what is the final position? The final position is 0 because it reaches the ground. The initial position is 20 because we're launching it from 20 meters. How much is the final velocity? We don't know that, but we do know the initial 0 velocity. Yep, that's 0. We just found it. So what is the acceleration? That's going to be minus t. And what is the time? We have no idea. So now we're trying to solve a problem in vertical motion, which is how long does it take to fall? Because the motion can be decomposed into horizontal and vertical components, we need to first realize how long does it take to touch the ground. Once we know the time it takes to touch the ground, and we can use that for the horizontal motion to actually describe when will it be. So let's start with the vertical motion and find out that. We're going to find the time when we don't have any information about the velocity. What equation do we use? Yes, v sub 0 t plus 8t squared divided by 2. So if we replace the numbers, final position is 0, initial position is 20, initial velocity is 0, times time, and minus 5t squared. So that's 20 minus 5t squared, it's equal to 0. Now there's many ways you can do the quadratic formula directly. So identify a, b, and c, and then use that. Or you can realize that this is simply 20, it's equal to 5t squared. Oops, no, 5t squared, which means that t squared is equal to 20 divided by 5, which is 4. And of course, t is equal to 2 seconds. So it takes 2 seconds. It takes 2 seconds to go and drop. If it takes 2 seconds to drop, then we can include that information in there and find, hey, what's going to be the final position? Well, the final position is going to be, that's x times t plus acceleration in x t squared. Well, what is the initial position? That's 0. What is the initial horizontal velocity? 15. What is the time? 2 seconds plus. What is the acceleration in x? 0. So how much is that? 30 meters. So what is the final position? 30 meters. So what is the answer? Answer D. A point on the rim of a 0.25 radius rotating wheel has a centripetal acceleration of 4 meters per square second. Radius being 0.25. What is the angular speed of the wheel? Okay, so how do we figure out this one? Well, the question that we know is that the centripetal acceleration is the velocity squared divided by the radius. So, and we also know that the omega is related to, excuse me, that the velocity is related to omega with radius. So of course, there's two ways of going. You just replace that in there. if you know actually the equation directly. You plug it, but the equations in the formula sheet contain this one and contain this one, so they'll contain everything that you need. So let's solve first for velocity. Velocity is going to be acceleration centripetal times radius square root. So that's going to be the square root of 4 meters per square second times 0.25. How much is that? That's the square root of 1, so that's 1 meters per second. So once I have that the velocity is 1 meters per second, then I can find that omega times radius is equal, or rather, let's replace numbers. Velocity is 1, omega, we don't know, radius 0.25. So omega is 1 divided by 0.25, which is 4 radians per second. So 4 radians per second, option D. Imagine a car driving in a circle speeding up. So we have a car and it's driving in a circle. And the car is speeding up. Is the car experiencing any acceleration? If so, what kind of acceleration is it experiencing? Again, another question of theory. There are two types of acceleration. We have centripetal acceleration and then we have tangential acceleration. We know that the centripetal acceleration, which is v squared divided by r, is actually the one responsible for curving the trajectory. So it changes the direction. Vectors have both direction and magnitude. What about the tangential? I've said this a million times. My tangential is responsible for speeding up, and that's obviously alpha r. So now the question is, what types of acceleration are? Well, we're moving in a circle. So every time we move in a circle, we have centripetal acceleration for sure. But we're also speeding up. And to speed up, you always need a tangential acceleration. So what do you have? You have both AC and A sub t. Option D. On a sunny Florida day, you're driving at a constant speed in your fancy convertible with the roof retracted. If you throw an object straight up, ignoring any resistance, where does so you're here, and then you just throw an object. And then a lot of time later, is your fancy convertible, as you can see, very fancy indeed, and the object falls. And so I'm saying, if you throw an object straight up and ignoring air resistance, where will it land relative to you? Well, the principle of inertia says that an object retains its motion with constant velocity in the same direction unless upon it is acting a force. There's no force in here for the object, and the object starts with a motion in the horizontal component, which is the velocity of the car. So the final velocity for the object, when there is no acceleration, you can do it. We don't know anything about x or x sub 0 for that matter. That's not important. But we know that the final velocity, we know the initial velocity is the velocity of the car, and we know that acceleration in x is 0. So what we can know is that any time later, let's say 1 second, we're going to know is the final velocity is going to be v sub 0x plus a times t. Because this is 0, the velocity is always the same as the initial. And because it's going with the same velocity as the velocity of the car, the object is going to fall exactly in your hand. If you fire a gun, which experiences the greater force, the bullet or the gun? Well, beautiful question that says third law of Newton. What does Newton says? What A does to B, B does to A. Well, A is the gun, B is the bullet. Who each experience the same, the force, the largest, that's law 1. Don't confuse that force is mass times acceleration, so indeed acceleration is going to be inversely proportional to the mass. But the force needs to be the same, because what A does to B, B does to A. So option C, theory question. A wooden block of 1 kilogram slides down an inclined plane at a constant velocity of 6 meters per second. What is the coefficient of kinetic friction if the plane makes a 45-degree angle? Well, let's see that. So from here, we're going to have this is probably the most difficult problem in the entire exam. So we're going to, because it's a little bit more elaborated, but it's actually trivial, we're going to have to break it into vertical and horizontal components. Vertical and horizontal components. So let's start with having the object. The object is stationary. Let's say now I'm taking the ramp and I'm just flattening it, right? And so I can see, well, we don't even need to do that, but vertical now, so nobody gets confused. Let's keep that like that. So what force is acting in here? Well, I have the weight, I have the normal, and I have the friction. So if I define x and prime y prime, then I'm going to use that. Y prime is going to be the vertical. So balance of forces in Y prime. What do I have? In Y prime, I have weight component in Y prime and normal component. So normal component minus weight in Y prime, it's equal to mass times acceleration in Y. But there is no acceleration in Y, so that's 0. That means the normal force is the same as the weight in Y. Okay, what about the horizontal? So now, horizontal is in this direction. In the horizontal, I have friction, and I have what? I have the x component of the weight. So then I have weight in x prime. So I can make the balance of forces. The balance of forces is going to be weight in x prime minus the friction, and that's equal to mass times acceleration in x. But here's the thing, what is the acceleration in x? A wooden block of 1 kilogram slides down the inclined plane at a constant velocity. If velocity is constant, acceleration is 0. Acceleration is 0. Force of weight in x prime is the force of friction. So let's now take the weight and analyze how to distribute. Weight works like this, and so we have x prime and we have the y prime. So with respect, because this is 90 degrees, that angle, 45, that angle is also 45 degrees. If you're gonna see it again, just take this one, that's 45, therefore this is 45, then that's 90 minus 45, that's 45. In this case anyways, it's trivial because it's 45 is its own complementary. But that's going to be 45 degrees. So the f sub y is going to be given by the adjacent. So that's going to be the weight times the adjacent. Whereas the weight in the x component is going to be the weight opposite. And the mass of the object is 1 kilogram. And we can take g to be 10. So the weight in y, it's going to be, well, actually we don't even need to calculate that. Let's keep it as it is. Let's realize that the question is, what is the kinetic friction coefficient? Friction, it's given as mu sub k times force normal. But friction is also equal to weight in x. So I'm going to have that friction, it's also equal to weight in x prime. Okay, what is the normal force? That's weight in y prime. So what I find is that mu sub k times weight in y prime, it's equal to force of weight in x prime. If we replace, we have mu sub k times mg sine of theta equals to mg, that's cosine of theta, mg sine of theta. M's and g's cancel, and mu sub k, it's equal to the tangent of theta. Why? Because it's sine divided by cosine. And what is the tangent of 45? That's equal to 1, because its sine and cosine are the same. If you don't have calculator, it doesn't matter. So what is the answer? Answer D. A 15 kilogram car rounds an embanked curve with a radius of 50 meters at a speed of 10 meters per second. What is the minimum coefficient of friction it must exist between the road and tires to prevent the car from slipping? Well, we're going to have a car and it's trying to make a turn. To be able to make the turn, it needs to have a centripetal acceleration. That means it needs to have a centripetal force. What's the force? Friction. So the question is, how large needs to be the force of friction such that the acceleration is the centripetal acceleration? So v squared is 100 divided by the radius 50. That's equal to 2. So we need to have an acceleration of 2 meters per square second. The centripetal force anyways is going to be mass times acceleration, centripetal. And that's going to be equal to the friction, which is equal to mu sub k times force of normal. If I take the car and analyze the car standing on the ground, I'm going to have a force of normal due to the ground, and I'm going to have a weight due to the car. Because there's no motion vertically again, this is 0, which means that the normal is just simply the weight, which is mg. So when I go here, I can replace and say mu sub k is mg. And so I can find now, finally, that I have mu sub k mg equals to m times acceleration centripetal. Don't need the masses of the car actually. Mu sub k, it's the centripetal acceleration divided by g. Because centripetal is 2 and g is 10, this is 0.2. That's 0.2, option B. You hold a heavy weight stationary above your head. Are you doing work on the weight? Are you doing work on the dumbbells, let's say, when you're in the gym? We've seen this a million times before as well in class. Are you doing any work? Well, work is force times displacement. Because it's vertical displacement, we can say delta y. What is the displacement? 0. What's the work? 0. So are you doing any work? No, because the weight is not moving. Trivia. Variation of this. A very light cart of 30 kilograms box moves at a constant velocity at a level of 15 meters, at a level 15 meter surface. So we're making a distance of 15 meters. This is level, so we don't have to decompose as an inclined plane. And what is the net work done during this motion? So again, it's force times delta x. What is the net work done during this motion, right? A very light cart of 30 kilograms moves at the velocity which is constant across. So every time I hear constant velocity, my mind jumps immediately to understand that if velocity is constant, the change in velocity is 0. And acceleration, which is the ratio of the change in velocity in time, is 0. But because I know that the force is mass times acceleration, when acceleration is 0, how much is the force? 0. So how much is the force? 0. So how much is the work? 0. I don't do any work on the object. A 100-gram bullet moving at 1,000 meters per second is fired through a 1 kilogram of wood, emerging from the block at the speed of 100 meters per second. If the block was originally at rest and is free to move, what is the resulting speed? So conservation of momentum. We have the block and we have the final scenario, which is going to be the block and the bullet. So the block, original velocity 0, the initial velocity is 1,000. Final velocity of the bullet is going to be 100. The final velocity of the block, we don't know. Conservation of momentum, initial and final. Why is conservation of momentum and not conservation of energy? If you use conservation of energy, you're missing portion, because kinetic energy is not conserved in this scenario, because to go through the block, you are destroying the block. There's going to be heat and there's going to be elastic potential energy. So you cannot say kinetic energy is conserved. It is not, in fact. So if you do that, you're going to find wrong results. So initial velocity is going to be this plus velocity of 2 mass 2, obviously initial, and needs to be equal to the final. And the final, of course, is the velocity of 1 mass 1 plus velocity of 2 mass 2. What is the velocity of 2? This is 0. The velocity of 1 is 1,000, and the mass of the bullet is 0.1 because it's 100 grams. And the mass of 2 is 1 kilogram. So that's going to be equal to 0.1 times the velocity at the end, which is 100, plus the velocity of 2, which we don't know, times 1. So this is 10 and this is 100. So we're going to find 100 minus 10, which is 90, is equal to V2. So what is the velocity? 90 meters per second. Option B. Travis sits on a stool that can rotate freely. He is initially stationary while holding a bicycle spinning clockwise. If he flips the bicycle wheel over, so its rotation reverses direction, it's now counterclockwise, what happened to Travis? On the stool, there's a issue in there. Okay, what happens to Travis? We've seen this in class and we've seen this with Travis. So the wheel, at first he is stationary. So Travis, let's say Travis is number 2. And the wheel, we can call the wheel to be number 1. And there's the bar with the wheel, and Travis is handling the thing. And he's sitting on the stool that it's also free to rotate. So this is in this platform that was rotating. And that thing is rotating, okay? And so the question is, well, at first, we actually should maybe do this like this. So this object is rotating actually like this, right? In the plane. So we're gonna be observing is first, at the beginning, angular momentum, it's equal to omega times I. So we're gonna see what is the conservation of angular momentum is given by the rotational impulse, but there's no external force, so there's no change in rotational momentum. Angular momentum at the beginning needs to be the same as the end. Initially, we don't even need to use numbers, but initially the wheel is turning clockwise. So let's say the clockwise at 1 radian per second. So omega 1 is 1 radian per second, right? But that's positive. And at the end, the wheel is counterclockwise, right? Because it's counterclockwise, let's say it's the same velocity but negative. And so I'm going to have the Travis inertia times 1 plus, wheel inertia. Conservation of momentum says that inertia of the wheel times the velocity of the wheel at the beginning plus inertia of Travis, velocity of Travis at the beginning, but Travis is not moving, so that's 0. That needs to be equal to will at the end, inertia is the same, it doesn't lose mass, plus Travis inertia, velocity of Travis. Because this is positive and this is negative, the only way of making this work, if this is, let's say, 1 and this is minus 1, the only way of making this work is to make this larger than 0. Because inertia is always larger than 0, omega Travis needs to be larger than 0. That means the Travis needs to be clockwise spinning, because otherwise momentum would not be conserved. So again, this is without the numbers, we can observe and see clearly that the only answer for this is that the Travis starts compensating, moving in the direction that originally the wheel was spinning. And that completes the midterm work.